Okay, welcome everyone. This semester we are going to discuss MATE 5201, Advanced Calculus. The scheduled time is Monday, Wednesday from 8:30 a.m. to 9:50 a.m. Each time 1 hour 20 minutes. And so far, let's see the textbook. The textbook, this is textbook. Okay, you can find the electronic edition online. So it's called Introduction to Analysis, third edition. The author is William R. Waite. Okay. Okay, so the textbook. Introduction to Analysis. Third edition. The author is William R. Waite. Okay, so this is the textbook. We're going to go through the textbook section by section, see how many sections we can cover. And for the semester, we will have two exams, midterm and the final. The midterm exam plus the final exam. The midterm exam is scheduled on October 15, Thursday, 5 p.m. to 7:30 p.m. Okay, so this is midterm exam. Final exam to be determined. Okay. Okay, and for the final grade, midterm exam and the final exam, they are 50-50 for your final grade. Okay, so this take 50%. Midterm take 50%, and final exam also take 50%. The final grade, 85 and above is A, 75 to 84 is B, 65 to 74 is C, 60 to 64 is D, below 60 is F. Okay. And also for each section, I'm going to assign some recommended exercise. I will not grade them, but if you have question, you can send me email, we can discuss. And midterm and final exam will have problems similar to the recommended exercise plus a material discussed in the exam, in the textbook. Okay, so midterm exam and final exam will have some similar problems, not brand new problems. So if you can understand the lectures well and you can do the problem recommended exercise, you should get a good grade in the final grade. Okay, so this is the basic stuff. Yeah, my email. Email lin.shan@upr.edu. So you can send me email to get whatever you want. You're interested. but I do not have like the fixed official hour. If you office hour, I do not have fixed official office hour. If you have any question, just send me email. Okay. Okay. lin.shen@upr.edu. Okay, so that's the basic information about the class. Yeah, for this semester possibly it's not useful, but my office C119. This is my office. Possibly this semester is not that important. Anything else? Let me think. Yeah, possibly that's it. Okay, so go online and try to find the textbook, and we will follow the textbook, and possibly the recommended exercise will be selected from the textbook. So it's important for you to have this textbook. Okay, so let's start today's discussion. We will not discuss a lot for the first lecture. We will only talk about some basic stuff, simple, to really start it. Okay. Chapter 1. The real number system. So this is a very familiar area, but some topics may not be familiar to everyone. Something maybe you take it for granted, but you don't understand what is behind it. So let's try to understand this real number system. The section 1.1, ordered field axioms. Okay, ordered field axioms. We will understand what is ordered and what is a field axiom. We know that's just basic rules. Okay, so we want to study the algebraic structure. So we want to study the algebraic structure of the real number system. Okay, so first we will set up the standard set theoretical notation. So empty set this notation is empty set. You put a 0 and cross it. It's empty set. And if this is 1, if A is an element of the set capital A, we write A in A, A in A. And if A is not an element of A, we write A is not in A. Okay, A is not in A. And to write a set, we can either directly write each element, or we can write some conditions. For example, if we have a set, we can write the set containing, if the set contains 1 and negative 1, so we can write this way. So A is equal to 1 and negative 1. Or we can write the condition like this: a is equal to x, x satisfies x squared is equal to 1. Okay, so that's how the way to write it. Well, it's not. Okay. 5. A is a subset of B. So in the notation, it's A is a subset of B if and only if every element of A is also an element of B. Okay? So this is a subset. Okay, and second, if A is a subset of B, but there is at least one element B in the set B that does not belong to A. We say, or we call A proper, so we add this one, a proper subset of B, a proper subset of B. Proper subset, we just use this notation without equal. So here we put this horizontal segment to mean A could be equal to B. But this place, you remove that horizontal segment, means A cannot be equal to B because this element B in B does not belong to A. Okay? And two sets A and B are equal. So how do we say they are, how do we know they are equal? Equal, we will write, of course we write A is equal to B. If and only if A is a subset of B and B is a subset of A. Every element of A belong to B and every element of B belong to A, then they are equal, right? So it's pretty straightforward. And a set A is called non-empty if and only if A is not equal to the empty set. Empty set contains nothing. There's no element. There's no element, then that's an empty set. Here, if it's not equal to empty set, then it will definitely contain something. If it contains something, it's non-empty, right? Okay. So we just try to set up the standard set theoretical notation. Next. The union of two sets A and B is the set of elements X such that X belongs to A or B or both. Okay, it belongs to A or B or both, then we say this set is a union of A and B. Union, we write A cup B. A cup B. A in the latex it's a simple. This one, A cup B, the union. Okay, so 10. The intersection of two sets A and B is the set of elements X such that X belongs to both A and B. Okay, so it must belong to both A and B. So here, that's why we write it A cap B, A cap B, A intersect B, A cap B. Okay. Okay, so that's a union intersection. Let's see what is a complement. The complement of B relative to A, the complement of B relative to A, here we write complement, not inside B. Relative to A means inside B, so A minus B. So technically it's A minus B. Inside A but not inside B is the set of elements X such that X belongs to A but does not belong to B. It belongs to A but does not belong to B. For example, let's check. Assume we have A is equal to -1, 0, and 1, and B is 1 and 2. Okay, so we use the basic example. We have two sets. Then what is A union B? A union B just get every point, every numbers, -1, 0, 1, and 2. Just collect all the points. A intersect B, just check which number is repeated. So here there's only one. 1 is repeated. Okay, so A intersect B is 1. And the complement of B relative to A, you see, you just remove the repeated element from the first element. So 1 is repeated, so it's equal to 2. It's inside the first element, first set, but not inside the second set. 1 belongs to the second set, so you just remove the common terms. And of course, you can switch the order. The same thing, you are going to repeat you are going to remove the repeated element. 1 is repeated. After you remove 1, so you have this. So it's like that. It's like the subtraction, but it depends on the order. It depends on this one. The complement of B relative to A and the complement of A relative B are different. Okay. Okay. 12. The many stuff. So we have, let X and Y be 2 sets. The Cartesian product. The Cartesian product of X and Y is the set of ordered pairs defined by X product with Y is equal to, by definition, it's ordered pairs X and Y such that X belongs to X, Y belongs to Y. So every element. Okay, and in the textbook they put 2 dots here. 2 dots means this is a definition. It's not the conclusion, it's a definition. Equal by definition, or it's defined to be. Okay, so this symbol means equal by definition, or is defined to be. You will only see this symbol in the definition. It does not come from the conclusion or the deduction. Okay. And when you have the Cartesian product, you have to be careful about these ordered pairs. You cannot exchange the order. Okay, so if X, Y, Z, W both belong to the Cartesian product, then X, Y is this element. This is an element in the Cartesian product. The X, Y is equal to ZW if and only if X is equal to Z and Y is equal to W together. Okay, so it's the equality of the elements in the Cartesian product. Next, after we have sets, after we have the Cartesian product, we can define the relation and the functions. So 14, let X and Y be sets. A relation on the Cartesian product X cross Y is any subset of X cross Y. Any subset of X cross Y is defined to be a relation. Okay, so let capital R be a relation on this X cross Y then we define the domain of R is the collection of is a collection of X in X such that XY belongs to the relation R for some Y. In Y. Okay? So the domain just means you collect X. You do not collect a Y. Okay? So the collection of the first coordinate is called the domain. 15. So with the help of the domain, we define a function. A function f from x to y, we also write this way, is a relation. So first of all, in this definition or in this textbook, they use relation to define a function. So function is a special relation. Is a relation on x cross y whose domain is x. So for the general relation, its domain may not be the whole x, but for a function, the domain, this special relation, the domain must be the complete x. Such that it's not the unique restriction, there's another restriction, such that for each x element x in the set X, there is one and only one y in Y that satisfies x, y belong to the relation f, or belong to the function f. Okay, so this is a definition of function. This is a complete definition of a function. Okay, and let's say domain is x. We can also say that f is defined on the set X, and y is called the value of f at x. The value of f at x. X is related to y. X, y belong to this relation. Okay? And for this special relation, for this function, two functions, let's put it 16, two functions fg are equal if and only if, so they mean the same relation. So what does it mean? It means they have the same domain and the value. Okay, i.e. same domain means the domain F is equal to domain of G, and the same value means Fx is equal to G of x for all x in X. Okay, so it's the same domain, same value. Okay, so those are the basic theoretical set notations plus the definitions. And in this textbook, the author tried to use relation to define the function. This is one of the language. We know that the function has many different interpretations, but the important thing is that for each x, there is only one y related to it. So that's an essential restriction. It doesn't matter what language you choose, but you need to fix that every x there is only one y related to it. So that's why it is the value. Okay? Okay, so after the theoretical notations, let's list the so-called the field axioms. We will explain it quickly. So this is called postulate 1. Postulate 1 is called field axioms. Field axioms has 1, 2, 3, 4, 5, 6, 7, 8. Well, there are 8 conditions. Okay, let's list them one by one. So there are functions. This one first function and the second function, addition and multiplication, defined on the Cartesian product, the set of real numbers cross real numbers. So this symbol you see here is defined to be R cross R, that satisfy the following properties. There are 8 properties for every A, B, C in R. Okay, so let's list all 8 properties. So the first property is a closure property. Closure property says these two functions, addition, multiplication, is closed inside the real set. So A plus B and A times B belong to R. Okay, so it's not like the other sets. For example, if we talk about irrational numbers, we know that irrational numbers, square root of 2 is irrational. 1 over square root of 2 is also irrational. But when we do the product, it becomes 1. This one is irrational. So this product is not closed for the set of irrational numbers. But for any real numbers, the product and addition belong to that. Okay? But here, this is just a field axioms. We need to verify all 8 properties. This one is just a counterexample. Okay? So the set of irrational numbers does not satisfy the first closure property. And second, associative property. The associative properties means addition, you can add the last two numbers or you can add the first two numbers, you do not get different value. The product, you can do product for the last two numbers or you do the product for the first two numbers, you have the same value. So this is associativity. Okay. And three, commutativity. Commutative properties. The commutative properties means you have A plus B and B plus A, they are the same thing. A times B and B times A, they are the same thing. Okay, the third one. And four, distributive law. Distributive law means if you get some mixed operation, A times B plus C, you can distribute A into the sum, you get A times B plus A times C. Distributive laws. Okay. 5, the existence of additive identity. Existence of the additive identity. It means there is a unique element called 0 inside R such that 0 plus A is always equal to A for all A in R. So identity means it does not change the other element when you apply the function. It does not change. Okay. 6, this is for the addition, and we have multiplication and multiplicative identity. Existence of the multiplicative identity. It's similar. The sentence is similar, except you change this. Operation plus you have some restriction about the 0. There is a unique element 1 in R such that first 1 is not 0, so 1 is not equal to 0. These two identity must be different. And second, 1 times whatever element is equal to the element for all A in R. So you see it's similar. In the addition, the function does not change the value of does not change the second value. Multiplication, the function does not change the second function, second value, second input value. Okay, so that's a identity. What identity means. Okay, and when we have identity, we can have so-called the inverses. Existence of the additive inverses. No, the additive inverses. So for every x in R, there is a unique element negative x. We write it like negative x, such that x plus negative x is equal to 0. So you can always have, it's a balanced element so that the sum of those two elements is equal to the additive identity. So that's a so-called, we call it inverse. You will see that all these properties are just abstract description of the number operations. Okay, so the next one, the last one, the existence of a multiplicative inverse. Existence of multiplicative inverses. Multiplication has a small difference because we know that 0 has no inverse, no multiplicative inverse, so we have to remove 0. So for every x belong to R but not equal to 0, non-zero element, there is a unique element x inverse belong to R, the 1 over the reciprocal of x, such that x times x negative 1 is equal to the multiplicative identity. Right? So this is the basic axioms for the set of all real numbers. And for the first time, let's stop here, and we will continue the discussion in the next lecture. I will upload all the lectures to the YouTube in the same place. You can check the videos. Okay, so that is the first section, first part of the lecture. Thank you. So we will continue next time.